Hello. In this series of exercises, we have been considering this quantity. We have seen that if the xi in this expression are identical and independent random variables, then this expression is an accurate estimator for the variance of the random variable X. There is a problem, however. If we are just given a series of samples from the distribution, then we do not know the expectation exactly. It is thus not possible to use this estimator for the variance. In this video, we thus want to consider whether or not it is a good idea to use the following as an estimator for the variance. In other words, we want to know what happens if we replace the expectation in this expression with the sample mean, i.e. an accurate estimator for the expectation. We want to determine whether the resulting estimator for the variance is biased or unbiased, as only if the estimator is unbiased will it be accurate. To answer this question, let's proceed as follows. Let's first expand out the sum of squares in the bracket as shown below. We can then rewrite the single sum as three sums and take out all terms that do not depend on the summation variable outside of the sums. We now note that this sum here is just the sample mean, and that the sum over n of all these ones is n. N then appears on the numerator and denominator, so the x bar in the last term here is just being multiplied by 1. What we thus find is that we can rewrite s squared as follows. Furthermore, if we use the definition of x bar given above, we can rewrite this as shown here. The expression for s that we just arrived at is shown here. Let's now consider the expectation of this quantity. The first term here is easy, as the expectation of the square is taken within the sum. This is thus the expectation of the random variable x squared as shown here. The second term is more difficult, as we must first multiply out the square before taking the expectation. We are helped, however, if we remember the expression for the variance of the sample mean that we learned during the last video, and which is shown here. Notice that this term here is the second moment of the distribution for the sample mean. This term appears again in the expression for the variance here. We can thus rearrange this expression and replace the second moment that appears in the sum. We thus arrive at the expression shown here. The first two terms in this expression are good. We would expect these in an expression for the variance. It is this third term that is a problem. This is a bias. The quantity that we have just calculated is thus a biased estimator for the variance, and it is thus inaccurate. All is not lost, however. We can rearrange the expression above to give the following. If we bring these two terms over a common denominator of n, we then arrive at the following. This expression relates the expectation of our estimator of the variance with the true variance. We can thus rearrange this and arrive at a simple correction on our estimator. This correction, which is called the Bessel correction, converts our estimator of the variance into an accurate estimator of the variance by accounting for the bias. To summarise then, we have in this video explained that we could get an unbiased, i.e. accurate, estimator of the variance by evaluating the expression shown here. When we use this expression, we calculate an estimator for the second moment and an estimator for the expectation. We then subtract the square of our estimate of the expectation from our estimate of the second moment and multiply by the Bessel correction. It is important to note that the number n-1 that appears in the denominator of the Bessel correction is referred to as the number of degrees of freedom. In addition, notice that we can rewrite this estimator using the expression shown at the bottom of the slide. I personally don't like this way of writing the estimator, as you need to write two loops if you use it within a Python program. Within the Python program, the first of these loops evaluates the sample mean x bar, and the second loop then accumulates all the xi minus x bar values squared. If you use the first expression on the slide instead, you can evaluate the sum of squares of the variables and the sums of all the variables using a single loop. You can then evaluate s squared after the loop. I hope that is reasonably clear, because in the programming exercises, you're going to have an opportunity to use this expression to estimate the sample variance. Thanks for your attention and good luck.